So inverse trig and integrals, right, you need to be able to recognize those basic patterns from their derivatives, but sometimes they're not as straightforward as you think. So I'm just going to go through a couple of examples of when you kind of have to use more advanced techniques to get those trig integrals, those inverse trig integrals to pop out. So the first one I'm going to do today is the integral of dx over x squared minus 4x plus 5. Okay, so if you're just looking at that, you're probably like, there is no way this is an inverse trig in it. And I'm telling you that you're wrong. There's actually an inverse trig function that's going to pop out here. So if we're just looking at the denominator, right, there's no way to do a u sub right now and get that u to balance out with a du, right? So that's not going to work for us here because the obvious choice for the u would be the denominator, and then our du would be 2x minus 4 dx, like all times dx, and there's no way that that's working for us. And it's not factorable, right? It's not a perfect square trinomial, but we can make it into something that we can use. So when you have just like nothing in the top, right, just like a number in the top or whatever over a quadratic like this that's not a perfect square trinomial, you can complete the square and make this usable. So we're going to complete the square on the denominator, and this is y. So I'm going to make this y equals x squared minus 4x plus 5. I'm going to move this 5 to the other side. So I'm going to get y minus 5 plus blank is x squared minus 4x plus blank. So I want to add a number to both sides that's going to make the right side a perfect square. So I'm going to do 4 over 2, which is 2, and then 2 squared is equal to 4 again. So I'm going to put a 4 on both sides. So simplifying, that becomes y minus 1, and I can write the right side as x minus 2 all squared. So this becomes, looks like a weird little x minus 2 all squared plus 1. So now I'm going to go over here and rewrite my integral and put this stuff, I mean to cut, I meant to copy, over in the denominator. So this is why I did that. So now I have a variable portion squared plus a number being squared. In other words, this is arctan. Right, you got something squared plus a number being squared. So I'm going to do a u sub on the x minus 2 part, which means that my du is just dx. So if I go ahead and do a little substitution, I get du over u squared plus 1. So that's just going to become the arctan of u plus c, and then if I plug back in for my u, I get the arctan of x minus 2 plus c. Right, so hidden trig function in there, hidden inverse trig, even though it looked nothing like any of our inverse trig models. Right, so sometimes you just have to be a little bit tricky, pull some shenanigans, and completing the square is often a way that you're going to do that. So if something looks like it might not be able to be factorable, it might actually be a hidden inverse trig function that you have to complete the square with. So I'm going to do one more example, and I'm actually going to do a definite integral. Just give myself a whole new page here so we have plenty of room to work. So we'll do the definite integral of 3 over 2 to 9 over 4 of dx over the square root of 3x minus x squared. Okay, so again, you might be thinking, this is not factorable, this doesn't look like any of my inverse trig functions, but sometimes remember, they're sneaky. Trig functions are sneaky. So, right, if we look in the denominator, right, we have the square root of, granted there is an x next to the 3, right, but something minus a variable being squared. So because the squared variable is negative like this, and there's just a square root in the bottom, that's kind of signaling to me that this is almost arcsine. So let's make it into arcsine. Let's see if we can. So I'm going to go ahead and complete the square again. So I'm going to let y equal 3x minus x squared. And now I really hate completing the square when there's not a positive 1 in front of the x squared. It makes everything harder. So I'm going to make it positive x squared. I'm going to multiply both sides by negative just to make my life easier, and we'll fix it at the end. So now I'm going to reorder. I'm going to add my blank in so that way I know what to add to both sides. So this one's a little harder because the b value is not even. So, right, to fill in that number, I'm going to do my b over 2, and then I'm going to square it, and that's going to give me 9/4. So I'm going to add 9/4 to both sides. Okay, so that's going to give me negative y plus 9 over 4 equals x minus 3 over 2 all squared. I'm going to move my 9 over 4 over. And now I'm going to multiply all of this by negative 1 again. So now I get positive y is negative of x minus 3 over 2 all squared plus 9 over 4, which I can reorder to be 9 over 4 minus x minus 3 over 2 all squared. Whew, a lot of work for that. But now, the reason why we did all of that work, all of that fun algebra, is if I substitute in for that in my denominator, I have the arcsine format popping up, and it's amazing. It's amazing. Okay, so I'm going to do this with a little bit of manipulation here, so that way I don't have to worry about the fact that there is not a 1 in there, there's a 9/4. So bear with me, I'm going to do some algebraic manipulation. Okay, so I want to make that into a 1, so I'm going to pull a square root of 9/4 away, and that is going to give me 1 minus would help if I did this accurately, right? The reciprocal of it, right? And so I'm just doing that because, right, if I do 9 over 4 times 4 over 9, it gives me 1. So if I were to multiply through, it would be fine. Okay. So I'm just showing you how my brain works. You might be working this problem a little differently, and that is totally okay. So the square root of 9 over 4 is 3 over 2. 1 minus, I'm going to make this 2/3 times x minus 3 over 2, all squared in there. All right, so I have 1 minus something being squared because that's going to fit arcsine. And then my final little bit of manipulation here before I'm ready for my u sub is I'm going to flip that 3 halves in the denominator. I'm going to flip it out so it's no longer in the denominator. So I'm going to pull it out as a 2/3 since I'm dividing by it, right? Multiply by the reciprocal of it. So 1 minus this crazy looking group all squared in here. Okay. So I'm just showing you this because I don't like to memorize formulas that I don't need to, right? There are those formulas, if you've watched the previous video, right? There's those formulas about like general inverse trig patterns, so you might be able to jump right to your answer from here, but why memorize all of those patterns when you can just know the basic derivatives? Okay. So I'm going to make my u be the 2/3 times x minus 3 over 2. So if I take the derivative of both sides, I'm going to get 2/3 dx. I also don't know why that 1 equal sign line is so squiggly. My pen is malfunctioning, right? Oh, hey, look, we got 2/3 dx, so we're totally good. So I also want to switch the limits of integration. So if x is equal to 3/2, right, u is equal to 2/3 times 0, so u is equal to 0 there. And then my top limit is 9/4. So u is equal to 2/3 times 9/4 minus 3 over 2. So if I do a little bit of fraction work here, that is 9 minus 6 over 4. 3's are going to cancel, and I'm going to get 1/2 here. Boom. So the great thing about this being a definite integral, as long as I did my work right, is that I am going to be getting just everything in terms of u, and I don't have to sub back in with everything. So let's actually set up this integral so it looks a little better. So I got my limits of integration there, my du in the top, right? That's going to take care of the 2/3 and the dx. And in the denominator, I have 1 minus u squared. Okay, so I still have my structure down. Now it is a basic arc sine. So I'm going to do the arc sine of u evaluated from 0 to 1/2. So that's the arc sine of 1/2 minus the arc sine of 0. Okay, well the arc sine of 0 is 0, right? So remember, we're trying to find the angle that gives us that sine value, and sine is equal to 1/2 at pi over 6, so we get pi over 6 here. So my final answer is pi over 6.